Hello, the topic of this presentation is fatigue behavior of geometrically tailored component. I am Javad Razavi, and I will present the preliminary results of our study on this topic. Here you can see the outlines of this talk. First, we start with motivation for the topic, and then explaining the brief explanation of the experimental and numerical work, and resultant discussion, and at the end, conclusions of the work. Notches and notch geometries have various applications when it comes to the design of mechanical and structural components. Three main reasons for using them is for connections, for load transmission between components, and repairing crack or damaged structures. Here you can see some examples of the notch geometries that are in real life application. A bolted hinge connection in a metallic structure. Here we have a topology optimized upright of a race car where it has very complex connection points that are basically notches with different geometries, and ultimately a more advanced case of notches, which is the lattice structures. In the connection points we have the notches which have, depending on the morphology of the lattice, they can have different geometries and dimensions. Notches cannot be avoided in many structures and machines, and notch effects have been a key problem in the case of fatigue loading. Some examples are given here. It can be as simple as a thread root in a screw or a bolt, and it can go up to the topology optimized part, which are produced via additive manufacturing. Although notches can be very dangerous, they can often be rendered harmless by suitable treatment. Okay, let's see first what presence of a notch can do to a mechanical component. If you consider a simple plate where there is no geometrical discontinuity, the stress flow, which are shown by these red lines here, are quite uniform all along the width of the component, and their distance is constant. By adding a geometrical discontinuity to this geometry, here you have two examples of a circular notch and a simple case of a crack. We can see that the density of these stress flow lines are changing around the notch, and they are getting closer to each other at the vicinity of the notch. What does this higher density of the stress flow line do to the component? If we look at the stress distribution in these components, which are shown here with the gray area, you can see for the simple case of a plate without geometrical discontinuities, we have uniform stress all along the width of the component. But in the cases where we have geometrical discontinuities, the stress raises when you get close to the notch. And of course, in the case of fatigue, in the case of crack component, this is more intense, and we have infinite stresses ahead of the crack tip. One of the first persons working on this aspect and presenting an equation for this intensified stress and the raise of the stress ahead of the notch was Inglis. He proposed this equation, which gives you the maximum stress at the notch tip as a function of the far field stress and the dimension of the notch that you have. Considering an elliptic shape of the notch, we can have the maximum stress value by having the far field stress ahead of the notch tip. At the specific point of X that is shown in this figure, if you have a specific geometry, which is circular hole, where A and B are equal, the maximum stress is expected to be 3 times larger than the far field stress that is being applied to the component. When we have a crack, B tends to 0, and in that case, it shows that the maximum stress ahead of the notch can tend to infinite. Which is a well-known phenomenon that we know for the crack components. The stress at the crack tip tends to infinite. So a parameter has been introduced called stress concentration factor, which is the ratio of the maximum stress to the applied stress. There are different definitions of this factor. It can be based on the far field stress or based on the net stress at the net section of the component. There have been different practices to reduce this KT value, to reduce the concentration of the stress in the component and ultimately improve its mechanical behavior A simple example is this shaft that you can see these sharp edges in this circumferential shaft result in a high KT value because the stresses around the sharp edge of the notch are quite large. By introducing a fillet in that area, you can reduce the KT and ultimately improve its mechanical behavior, especially in the case of fatigue loading. But the question in this research comes to how to reduce the stress concentration factor without changing the notch geometry and the outer geometry of the component that we have. Well, let's review the materials and methods of this study. For performing the analysis, what we did was to add some secondary notches to the component without changing the outer geometry and without changing the main notch that we had, which was the center notch in the component. So the dimensions are given, and we have three different scenarios. In the first scenario, we have added a secondary notch of 3 millimeter in diameter on both sides of the main notch. And the variable is the parameter V, which is the distance of the secondary notches with the main notch. In the two other categories, which is notch 5 and notch 7, this number indicates the total number of notches in the component. Notch 5, it means that we have added 2 additional notches, 2 secondary notches on both sides of the main notch. And notch 7, it means that we have 3 added notches on both sides of the main notch. You need to pay attention to the fact that the secondary notches in these two scenarios, they are the outer point is tangent to the main notch. So we don't have the secondary notches behind or further away from the main notch. In these two cases also, the variable parameter has been considered to be V, or the distance between the secondary notch and the main notch. This parameter V in the first case has been considered to be 2, 3, and 4 millimeter, and in the other two cases has been considered to be 1 millimeter and 2 millimeters. So obviously we have two scenarios. In the first scenario, the secondary notch is quite large, still smaller than the main notch, so it is 3 millimeter. And in the second cases, we have smaller secondary notches, not to introduce too much of material loss in the component. And also the distances that we have considered are 1 and 2 millimeter instead of 2, 3, and 4 millimeter. So these are the variables. Then the samples were fabricated from aluminum alloy 5754, and the fabrication technique was CNC machining. The tensile properties of the material are given here. And the fatigue tests were performed under constant load of 4.5 kilonewton for all geometries with a loading ratio of 0.01 and loading frequency of 20 Hertz. The fatigue tests were performed under load control condition, and 2 specimens so far has been tested for each geometry, and the results have been presented in this presentation. Numerical analysis were performed using Abacus software. For that aim, a quarter of the geometry has been modeled. 8 node bilinear plane stress quadrilateral elements have been used for this simulation. Smallest element size has been considered to be 0.1 millimeter. Mesh convergence studies have been performed to obtain this value of the size of the element, and symmetry boundary conditions have been considered in the cut edges of the model. Let's look at the result and then have some discussions on them. After performing the stress analysis, we could obtain the stress variation within the component, both for the case of the control specimen, which is called notch 1, and the 3 categories that we had, secondary notches. As you can see, in all the cases with secondary notches, the stress concentration can be observed both for the main notch and the secondary notches. And looking at the stress distribution along the ligament of the specimen, we can see that in all cases, we had a drop of the stress value ahead of the notch. Of course, in the case of having only 2 additional notches on both sides of the notch, or let's say 1 on each side, in all 3 cases, regardless of what is the distance, the stress distribution was almost the same in all cases. And in the cases where we had 5 notches, which means 4 additional notches, 2 on each side, depending on the distance, we could have different stress fields ahead of the notch. Obviously, the notches that were closer to the main notch resulted in lower stress values. The same applies for the case of notch 7, where we had 3 added notches on each side, and where we had closer notches, we had lower values of the stress ahead of the notch. Comparing the notch tip stress values or the sigma max divided by sigma net, which will give us KT value based on the net section, we can see that there is a drop from almost 2.44 to a value of which is 2.18. So this drop is obvious in all cases. In the first category, the difference is not that high, but in the other cases, when we have the notch is closer to the main notch, we had a smaller maximum stress at the main notch, at the tip of the main notch. But let's see how much this reduction of the stress at the main notch tip can reduce or increase the fatigue life. Looking at the fatigue results for all different cases, we can see that for the control specimen, you can see the broken samples here. For the control specimen, the fatigue life was something around 100,000 cycles, and this value was increased up to 300,000 cycles in all cases, in some of the cases, which means 3 times more, 3 times higher fatigue life were obtained. So in the first category, when we had the secondary notch closer to the main notch, which was notch 3.1, we had the highest fatigue improvement. Although in the stress distribution, we couldn't see that much difference, but in the fatigue part, fatigue results, we can see the difference. And one of the main reasons that we can see this difference is also the driving force when the crack is propagating, and it would require further analysis to check that point. In the other 2 groups of notch 5 and notch 7, in both cases, we had improvement of the fatigue life, but in the case of notch 7, where we had notch 7.1, which is with lower distance between the secondary notches compared to the main notch, we had one issue with starting the crack from the secondary notch instead of the main notch. And that could be the reason that the improvement was not as high as the other cases. All in all these different cases, we had the fatigue improvement. And as you can see, we don't even need to have a secondary notch to be as large as the first category. In the second cases, the radius of the secondary notch was 0.75 millimeter, which is less than 1 millimeter, but still a significant improvement in the fatigue life has been obtained. This obviously would require further studies to obtain the same values for different loading levels. But the main goal for this work was to start from here and then go for design for additive manufacturing. In the main scope for design for additive manufacturing, we are going to use lattice structures to manipulate the stiffness and also the stress distribution in the component around the main notch, and ultimately reduce the maximum stress at the head of the notch tip and increase its fatigue performance. This is something that we are in the design and fabrication process, and soon we will start testing the components that have been geometrically tailored by incorporating the lattice structures in them. Tailoring can be considered as a valid design tool for geometrically complex parts produced via additive manufacturing. This initial study approves the extension of fatigue life of notch component, which were including additional incorporated notches. The level of local stresses in the part and consequently the fatigue life of the components are directly related to the size, location, and the geometry of the added notches. Further studies are required to properly specify the dimension factor for an optimum fatigue life of the part. Smoother stress flow and higher efficiency in case of complex loading scenarios are expected by using metamaterials as the tailoring tool within the parts. Thank you very much for your attention. Here, my contact is provided. You can also scan this barcode to have access to my Google Scholar and also my personal academic website. Thank you. Have a nice day.